Okay, let's unpack this. If you're involved in machine learning and specifically reinforcement learning, or RL, the absolute biggest challenge isn't just training an agent.
Not at all.
It's getting that agent to explore effectively. I mean, an agent can only learn from what it experiences, right?
Right. So if it gets stuck in one tiny corner of its world, it's never going to find those really high-performing behaviors.
The classic local minimum problem, but on steroids?
It is. It's like standing at the bottom of a small hill thinking you've peaked, but Mount Everest is just, hidden behind the next ridge.
So to solve that, researchers often turn to population-based methods. Instead of one agent, you train a whole group, a population.
Yeah, and the
Yeah.
idea is to efficiently gather this wide range of experiences. Things like neuroevolution or quality diversity are all built on this concept.
But if they're so great at gathering experiences, why do they still, hit a wall?
Because the way they measure diversity is, well, it's flawed, fundamentally. They reward agents for being different, but they don't stop the whole population from just reclustering in a new, but still redundant spot.
And that failure is exactly what our source material is all about today. We're doing a deep dive into this really powerful new approach called diversity via determinants, DVD for short.
And this research, it just completely reframes RL exploration. It injects some, frankly, beautiful mathematics and geometric thinking into how agents decide where to look next.
So our mission today is to walk you through the 3 core innovations of DVD. We'll start with why the old ways fail, this idea of redundancy and cycling.
And then we'll show how DVD fixes it. The result is dramatically better performance on some incredibly hard tasks. We're talking state-of-the-art on that notoriously difficult humanoid running task.
All right, so let's set the foundation. Population-based training. The appeal is obvious. Finding one good policy is hard. Finding a bunch of different good policies gives you robustness.
A wider net. Yeah.
But you said the way they measure diversity is flawed. What's the biggest structural mistake they make?
The mistake is thinking locally instead of globally. Traditional methods like novelty search, they work under what we call a mean field assumption.
A mean field assumption, meaning?
Meaning each agent is only worried about 2 things.
Yeah.
Its own reward and its pairwise distance from its immediate neighbors.
So it's just asking, am I far enough away from the guy next to me? It's not looking at the whole team.
Precisely. It has no concept of the collective spread. And this local view creates 2 just devastating failure modes: cycling and redundancy.
Okay, let's start with cycling.
Cycling is what happens when you reward novelty too much. The agents are incentivized to just constantly shift their behavior. They chase newness just for the sake of being new.
Then the cost of that constant churn is...
You never settle down. No single agent ever fully exploits a promising behavior that might lead to a huge reward. The research actually showed this. They tested standard novelty search on a simple task, a running robot. It completely failed.
Because it kept abandoning good policies.
It kept abandoning them because they weren't new anymore. It's the definition of cycling. It just never converged.
That sounds like a system working against itself. Okay, redundancy. I think I can picture this one.
Redundancy is easier to see, yeah.
Yeah.
Imagine you have 5 agents, but 3 of them are doing almost the exact same thing, and the other 2 are also clustered together.
So you have 2 groups.
2 groups. Now, because they're measuring the average distance between all pairs, that average might look deceptively high if the 2 groups are far apart.
But you're really only exploring 2 unique areas. You're wasting 3 of your 5 agents.
Exactly. You're occupying a minimal, useful behavioral space. So you've got these individual updates leading to cycling and redundancy. But there's a third problem.
Which is?
Defining what the agent is even doing. This is the behavioral characterization, or BC.
The BC. So to measure diversity, you need a way to describe behavior.
And older systems made you handcraft this. For a walking robot, the BC might just be its final XY coordinates.
That sounds okay for simple things, but very limited.
It's incredibly brittle. It kills generalizability. If you change the environment even slightly, say the reward is now based on momentum, that handcrafted BC is now useless. People spend so much time engineering these things.
And on top of all that, you have the universal pain point in RL, the hyperparameter. It all comes down to lambda, right?
Oh, yeah, lambda. The dial that says how much we care about reward versus how much we care about diversity. Exploitation versus exploration.
And that's usually just a fixed number you have to guess.
It's a fixed number, or it's based on some simple, inflexible rule. Set it too high, and you ignore rewards. Set it too low, and you just get stuck in a local optimal. It's trial and error, and it's a massive headache.
Right. The foundation is correct. Individual focus, redundancy, cycling, rigid BCs, and a brittle lambda. So let's see how DVD starts to fix this.
DVD starts right at the source.
Mm.
It kills the handcrafted behavioral characterization. Instead, it defines a task-agnostic behavioral embedding.
I love the sound of task-agnostic. That implies it works anywhere. How do they represent the policy without just looking at where it ends up?
Instead of an external metric, they define the embedding for a policy as the set of actions it takes across a finite set of states.
So if the policy is the brain, the embedding is like a transcript of that brain's outputs, the actions, in a few standard situations.
That's a perfect analogy.
Really?
It represents what the policy does across different inputs, not just where it ends up in one run. Now, since the full state space is often way too big,
Infinite, usually.
they use an approximate embedding.
And how do they make that approximation without making it brittle again?
They just sample a small fixed number of states. In the paper, they use 20 randomly selected states. Then they concatenate the actions the policy takes in those 20 states. This creates a vector, a signature that captures the policy's behavior.
Only 20 states. That feels arbitrary. How can that small sample really represent a complex policy?
And that's the really clever part. The research shows this is surprisingly robust. You don't need perfect fidelity. You just need enough variation to tell policy A apart from policy B.
So it's about the signature, not a full biography.
Exactly. It's derived from the policy itself. It's automatic, internal, and completely task-agnostic. That generalizability problem solved.
Okay, so now we have a good general way to define what an agent is doing. Now we get to the core of it, optimizing the whole population at once.
Yes, the new global loss function. It explicitly couples the entire population. It's the sum of all the rewards, plus this weighted diversity term.
And the magic is in how they measure that diversity.
The magic is the determinant of the inner-agent kernel matrix, the det-K.
Okay, I can almost hear our listeners tuning out at determinant and kernel matrix. Let's make this simple. This is the aha moment. Why is a determinant so much better than just measuring average distance?
It's a shift from measuring distance to measuring volume. Think geometrically. If you take all your policy embeddings, the determinant of the matrix they form represents the volume of the geometric shape they span in that feature space.
The volume. Okay, so let's go back to the redundancy example. I have 5 agents, all clustered together. The average distance between them is small. But what's the volume they occupy?
It's minimal. It's close to zero. Maximizing the determinant forces the population to spread out in a way that maximizes the total space they cover. If the volume is high, you know your policies are non-redundant. They're truly distinct.
That makes perfect sense. It directly punishes redundancy. If 4 of my 5 agents are basically the same, my volume is still tiny, even if the 5th agent is miles away.
Yes. Think of it like this. You hire 5 photographers to cover a city. If all 5 stand in the same spot, the volume of their combined coverage is 0. But if they spread out to 5 different neighborhoods, the volume they cover is maximized. DVD makes sure your agents spread out.
And the paper backs this up mathematically, right?
Yeah, they do. They used a simple environment, the tabular MDP, with 5 known optimal policies. They found the determinant was only maximized, only greater than 0, if the population was exactly that set of 5 diverse optimal policies.
And the distance metric failed that test.
It failed. Other clustered suboptimal sets could actually get a higher average distance score. It was fooled. The determinant is mathematically guaranteed to find true, useful diversity.
Okay, so redundancy and generalizability are solved.
Yeah.
But we still have that devilish lambda, the trade-off dial. How does DVD make that adaptive?
They just admit that fixing lambda is brittle, so they treat the choice of lambda as its own learning problem. They use an approach based on Thompson sampling.
A multi-armed bandit problem.
Multi-armed bandit. The different arms you can pull are different settings for lambda. So one arm might be lambda equals 0, which is pure reward focus. Another might be a high lambda for high diversity.
And the algorithm pulls an arm to see what works best right now. But what's the reward? How does it know if it made a good choice?
And this is the critical part. It's not rewarded just for finding novelty. It's only rewarded if that choice of lambda led to a better policy. Specifically, if the reward from the new policy is greater than the reward from the old one.
Wait. So the system is learning when diversity is helpful, not just when it's present.
Precisely. This is the key difference from novelty search. Diversity has to prove its worth. If the agent is on a good path, the system will probably pick lambda equals 0 and just focus on exploiting that path. It stops the catastrophic cycling we talked about.
And that takes so much guesswork off the researchers' plate. Did the experiments confirm this works?
Absolutely. The ablation studies show that adaptive lambda significantly boosted performance compared to a fixed lambda. It proves the optimal balance is dynamic. It has to be decided moment by moment.
So we have this really robust framework built on superior math. Let's get to the results. It was tested in 2 ways, right?
All right, a black box version, DVDES for evolution strategies, and a gradient-based version, DVD-TD3.
So let's start with DVDES on those hard exploration tasks.
The point V0 environment, classic deceptive local optimum. The agent has to go around a wall to reach a goal. Hitting the wall gives it a mediocre reward around NGET 800. That's the trap.
An easy, wrong answer.
Exactly. And standard ES and novelty search ES failed every time. They just got stuck hitting the wall. But DVD-ES, it solved the environment in all 10 seeds. Every single time.
Why?
The determinant. As the agents clustered near the wall, their volume went to 0. The global objective basically screamed, "Spread out!" This forced some agents into totally different behaviors, and eventually one found the path around.
It used diversity to literally break through the wall. What about the multimodal tasks, like the cheetah robot that has to learn to run both forwards and
A
backwards?
critical test. A good diversity method should find both modes. And DVD-ES did. It learned both forward and backward running. Standard ES usually just learns the simpler mode like backward running for the cheetah and then gets stuck. The determinant ensures the population finds and keeps both distinct skills.
And the opposite test. Environments with just one single optimal policy. The kind of task that breaks novelty search.
This is where it really shines. On single-mode tasks, novelty search just fails completely. It abandons good policies to chase novelty. But DVD-ES, with its adaptive lambda, performs just as well as vanilla ES. The diversity term only kicks in when it's needed. It doesn't disrupt success.
So it doesn't hurt performance when you don't need it.
In fact, it actually outperformed vanilla ES on Walker TechEnt, which has a known local trap. So its exploration is still useful for making sure you find the best single mode.
All of this was building up to the main event, applying this to a state-of-the-art method on the infamous humanoid V2 task.
Yeah, that environment is notoriously hard. So they implemented DVD-TD3 with a small population of 5 agents sharing information. The big trap here is a local optimum at 5,000 reward, which is basically just a survival bonus for standing still.
To get past 6,000, it actually has to learn to run.
It has to learn true, sustainable forward locomotion.
And the results compared to plain TD3, or even an ensemble of TD3s without the diversity term.
It was a huge leap. DVD-TD3 got both better sample efficiency and a much higher final score. Their median reward hit 61791.
Wow.
The paper notes that this was the first algorithm of its kind to break the 6,000 reward barrier in just 1 million time steps. Other methods, like soft actor critic, needed 3 million time steps to get there.
6,091. That is the difference between an agent just surviving and an agent actually succeeding at its task. It proves this isn't just theory.
It proves that measuring diversity as volume is a powerful, practical driver of performance in deep learning.
So, to bring it all home, this deep dive really shows how elegant math can solve these really frustrating practical problems in ML.
It's a full toolkit.
Right. It gives you a task-agnostic way to define behavior. It uses the determinant to ensure non-redundant diversity by maximizing behavioral volume, and it uses adaptive learning to balance the whole thing.
And the broader impact here is twofold. One, obviously, is performance. Better sample efficiency, better final results. But two, and this might be more important in the long run, is robustness. An ensemble of diverse agents is just inherently less likely to overfit or fail on some weird edge case. When you deploy these things in the real world, that kind of generalization and reliability is everything.
It's a compelling case for moving beyond these brittle, handcrafted metrics. But as I was reading, I noticed they often used a fixed population size, M of 5 agents, or sometimes M of 3.
Yes.
And you mentioned that on some tasks, like cheetah, a larger population actually performed worse than a smaller one.
That's right. And that brings up a really interesting question for you to think about. DVD figured out how to adapt the degree of diversity, the lambda. But what if the optimal number of policies changes from task to task? One problem might only need 2 good solutions, another might need 50.
So the next frontier.
The next frontier is adapting the population size itself. How would you design an algorithm that learns not just how much diversity to encourage, but how many truly distinct, high-performing behaviors are optimally needed to solve any given problem?